Fine. So see, look here. Right now we are trying to find out the electric flux, okay, due to a disk. Now look at this green thing. This green thing is with this green circle over here is basically the disk, and we have to find out the electric flux at this point P. Okay, I'm trying to explain again. I'll be doing it quick. The distance from this point P, okay, considering the fact that you brought a test charge over here, okay, test charge means it's nothing, it's just simply for your reference. And so you brought this test charge over here at this point P. The distance between the disk and the point P is D, okay. And now what happened is the radius of this disk is R. The radius of this disk is R. And the only way to find out, not the only way, but basically the easiest way to find out the electric flux is by taking a small element. And in this case, in the case of a ring, in the case of a disk, we will take a ring. And what we'll do is basically, we'll consider that this ring, this small ring element which we have taken, is having a distance of x from the center. I have written it over here, but you just assume, because there's no space, this red color ring which is there, it has a radius of x distance and it has a thickness of dx distance. I hope that is clear. We are taking a ring which is x distance from the center, or x having an x radius of x length, and thickness to be dx. Okay, so now we can directly jump. Once we understand this small diagram, we can directly jump. This, everyone please listen, because this is Gauss law. Okay, this is itself Gauss law. Understanding this will help you understand Gauss law much better. So we know that d phi is equal to what? EDA. Everyone is clear with that? D phi is equal to EDA. Okay, give me a please reply. You all can talk to me, no problem. Yeah, you all can talk a little bit loud. Okay, I'll just increase my volume also. So I'll like to have responses from you. See, look here. D phi is equal to E dot dA. Okay, and why it is d phi? Because we are taking a ring element which is dA. Okay, we are taking a ring element which is dA, a small element, and we know that dA is what? What is dA? 2 pi x into dx. Why 2 pi x into dx? What is 2 pi? 2 pi x. 2 pi x is basically circumference of the ring, and dx is what? Dx is going to be the thickness of the ring. Okay, because see, we are taking a ring element of thickness dx, x distance from the center, and dx distance is a small amount of distance that creates a ring around this disk. Okay, so 2 pi x into dx. Any doubt here? Please let me know. Okay, so now what we know, we have learned that E is equal to kq upon r square. Okay, kq upon r square. What does that simply mean? I'm just revising again. E is equal to F by Q naught, where F is the force felt by the charge Q naught upon bringing a test charge in the presence of a electric field. Okay, and so basically we get E is equal to kq upon r square. Now, once we know E is equal to kq upon r square, we can say that dE is equal to what? dE is equal to k dq upon r square. Yes or no? K dq upon r square. Yes or no? No response.
Yes, sir.
Yes, sir.
Yeah, please give me a response. At least I'll know I'm teaching to someone, no? And so dE is equal to k dq upon r square means, okay, if we put that in terms of d phi is equal to, what is E? K dq upon r square. Why k dq upon r square? Because we are taking a small ring element. So I'll write that k dq upon r square into 2 pi x dx. Am I right? Am I right? You understood this? Understood
Yes,
this? Yeah.
Yes, sir.
Now what is R? Tell me first. What is R? What is R over here? R square. What is
Root
R
over
square?
d square plus
Root d
x
square
square.
plus x square.
When you square it, what you'll get? When you square it, what you'll get? You'll get only d square plus
D
x square.
square plus
d
x square.
square plus x square.
Smart. Very nice. Okay. D square plus x square. Okay. This much you understood, everyone. I hope you all have understood this. Okay. So now what can we do now? What can we do? We can take we came to know what is d phi. We came to know what is d phi. We have to only integrate it. Okay. To know the fact what is phi. So what is phi here? Phi will be equal to what? Integration of d phi, which will be, remove all the constants out. What is constants? Look at this term here. What are the variables? X is a variable and dq is a variable. Am I right? X is a variable, dq is a variable.
Yes, sir.
Yeah,
Yes.
dq is a,
Yes, sir.
yeah. So, but what is the, tell me what is the entire charge over the ring then? Charge over the entire ring. I can take it as q, na? I can take it as q.
Yes, sir.
Okay, I can take it as q. See, if you all didn't understand, no problem. You forget the idea of dE. dE is equal to k dq upon r square. Just E is equal to kq upon r square. That is what you have put in this equation. Is this clear? Any doubts? This makes it easy, no? E is equal to kq upon r square. Okay, you put kq upon r square, instead of r you put d plus x square into 2 pi x dx. Okay, now take the constants out. K, q, okay, 2 pi is a constant, and then integration of x upon d square plus x square dx. Am I right? Am I right?
Yes, sir.
Yes, sir.
Okay, how, tell me how we all will solve it. Okay, I am rubbing the entire thing. Just you all know this, that integration of x upon d square plus x square. How will you all do it?
D square
What
can be
method?
written as
Sir, we can take x square plus d square equal to t.
So yeah, right. So what you will get? Phi is equal to, okay, integration
Sir,
of,
then
that is
we can differentiate on both sides. Then we will get the value of dt.
right. Okay, x upon d square plus x square, okay, dx. And so if I want to, I will take x square is equal to t. Okay, x square equal to t, then 2x dx will be equal to what? Dt. Okay, 2x dx equal to dt. So I will write that bit. Okay, so what I will get here? K q 2 pi integration of what is x? What is x? Tell me what is x?
root t.
So dt by 2.
Dt by 2. Okay, dt by 2. And what is d square plus x square? How can I write that? I can write d square plus t. Am I right? Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. One minute. Just give me a minute. Okay. We didn't consider one thing. What didn't we consider? Can you all tell me what we didn't consider? What we didn't consider? No response. We didn't consider cos theta, no?
DQ.
Cos theta.
Yeah, we didn't consider cos theta. So tell me what will be cos theta now? I will just write over here. Okay. What is d phi cos theta? What is cos theta? Over here.
X by d.
X by d.
Okay. It will be what? No, wrong, na? Adjacent upon hypotenuse, na? D
Upon
upon
root
d square plus x
D.
square, na?
Yeah.
So I will write that. Okay. I'll write that here. See, look here. D phi is equal to, I'll just adjust. So instead of this dx, I will write d upon d square plus x square. Am I right? Root of d square plus x square. And what I will get? I will get d square plus x square raised to 3 by 2. Am I right? And I will get a d out here. I will get a d out here. Right? No response. I'm not getting any response. Is everything right?
Yes, sir.
Yeah. So if we continue with this, if we yeah. if we continue with this, what we'll get, qkd2. Okay, I will just if I remove, okay, this 2 and this 2, if I remove, what I'll get dkq 2 pi by 2 integration of dt upon d square plus t square whole raised to 3 by 2. What gets cut? This 2 and this 2 will get cut. Am I right? Okay. What remains is this q k d dt upon d square plus t square. Okay. Is this clear? Any doubt?
Could you
Okay.
explain
Yes,
it
sir.
more, please?
Yeah. Someone is
Could you
asking something.
explain it? Could you explain it once more, please?
Yes. Yes. Okay. See this. From where you want me to explain? From d phi cos theta? Should I explain?
Yes, sir.
Okay, d phi cos theta is equal to what? What you got? First of all, what we got d phi is E dot dA, and E into dA. What is dA? dA is the area of this small red color ring. Okay, that is what 2 pi x, that is circumference into thickness, which will give you the area of the ring specifically. And so what we got, area of the ring is 2 pi x dx. Okay, so and ultimately then what we did, we substituted E as kq upon r square. Okay, kq upon r square, and what we got r as, we got r as the hypotenuse, right? That is d square plus x square. Understood this? D square plus x square. So
Yes, sir.
I wrote, yeah. So now what happened is, then later on I took x square is equal to t for x square. This x square is there. I have, first of all, I have taken the cos component now. See, because ultimately it is going to be in this direction. Okay, in this direction. I want it along this direction. So I will take the cos component of it. Okay, I got the flux in this direction. I want to take the cos component of it. So d phi cos theta is equal to kq 2 pi integration of x upon d square plus x square into cos theta. And cos theta in this is what? Adjacent upon hypotenuse. So adjacent is what? D. Okay, considering this is theta. Okay, this is d, and hypotenuse is root of d square plus x square. Okay, so I wrote d upon root of d square plus x square. Okay, then I have taken x square is equal to t for simplification of integration. Okay, so 2x dx is equal to dt. Differentiate both sides. So ultimately, I have substituted over here that x square as t, and that is what I have written, x square as t over here, and I have taken x as what? X I can take as dt upon 2. Is that clear?
Yes, sir.
Yeah. So if any doubt, anyone, please let me know. Okay. So then what I took the constants out from here. 2 is a constant. I removed it out. 2 and 2 got cancelled. What remained is dkq integration of dt upon d square plus t square raised to 3 by 2. Integration becomes very simple now. Okay. I'm just rubbing everything off. Just understand the concept. Rest everything will become very clear. After this, we are studying. Immediately, we'll be getting into the Gauss law and Gauss application. Okay. So what remains is equal. Okay. Q K D. Okay, Q K D into integration of what it was, dt upon d square plus t square raised to t,
Well,
right?
d square
T,
plus t.
yeah, remind me, no problem. Raised to 3 by 2. So do the integration now. How will you do? Better to do in what way you will do? You just take it up. Okay, you will take it up. So there's another term over here. It's going to be pi. Okay, so you will take pi q kd integration of d square plus t whole raised to minus 3 by 2 dt, and that will give you pi q kd. What is the integration of this? You will get what? D square plus t minus 3 by 2 plus 1 upon minus 3 by 2 plus 1. What you will get with this? What will you get? You all are solving? Anyone solving? Okay, you will get
1 upon
q,
root under d square plus t.
yeah, you get qk pi d. Okay, if you directly do it, you'll get minus 2 upon, okay, t plus d square raised to 1 by 2. Am I right? Any doubt? Minus 3 by 2 plus 1 is what? Minus half. Minus 1 by 2.
Yes.
And this also will become minus 1 by 2. Okay, this becomes minus 1 by 2. Reciprocal will be minus 2 upon, you will take t square plus d square raised to half. Am I clear? Okay. Now, you tell me, what are going to be the limits? Fast, quick. What are going to be the limits? No response. What are the limits?
Zero to
What are the
R.
limits? 0 to r. Yeah, why so long? 0 to r, no? Why? Because we are going to expand this ring and contract this ring. At x is equal to 0, you will get a small ring over here. At x is equal to some distance, you will get this ring over here. At x is equal to maximum, you will cover the outer part of this disk. That way, what you are doing is basically you are finding out the entire area of the disk. Okay, you are finding out you are integrating over the entire disk. Okay, so 0 to r. So what you will get? Fatafat, tell me. Q, K, pi, d. You'll get minus 2 upon d square
E square plus
plus
X
r.
square under root.
Yeah, what is x square? R square. Am I right?
Yes, sir.
Yeah. So raised to 1 by
Yes,
2.
sir.
Minus or minus will become plus 2 upon d square plus r square. Again, it will be sorry. Yeah. It will become 0 na here. Am I right? Is this understood?
Yes, sir.
Yeah, you all are getting it? Yeah. So, okay. Now what is the entire thing going to become? What is the entire thing going to become? If I remove 2 out, I will get 2 q k pi d. Okay, and I'll take d inside. If I take d inside, what I will get? Forget d, don't take it now. Let's solve it first. Minus 2 upon d square plus r square raised to 1 by 2 plus sorry, I'm taking 2 out, so I'm going to get 1 here, minus 1. And what I'll get? 1 upon d square raised to half. That is how much? That's 1 upon d only, no?
Yes, sir.
So what I will get now here, look here. I will get 2 q k pi d. Okay, I will just twist the terms. I will take this term over here, this side for simplicity. So I'll get 1 upon d minus 1 upon d square plus r square raised to 1 by 2. Okay, d square plus r square raised to 1 by 2. I just did one thing. I just took this 1 by d over here. I put it this side, and this term I have taken it that side, just for simplicity. Now if you take d inside, what you'll get? If I take this d inside, it will get multiplied. This d, if I remove it, I multiply it over here d, and it will become d over here. D upon d, you'll get 1 minus d upon d square plus r square raised to half. Is that correct?
Yes,
Yes,
sir.
sir.
And what I can write k as? K I can write as 1 upon 4 pi epsilon naught. So pi and pi gets cut. This will get divided by 2. What will remain here? Q upon 2 epsilon naught. Q upon 2 epsilon naught.
Yes, sir.
Oh, okay, so I'll write Q upon 2 epsilon naught. So now you tell me, d upon d becomes what? 1, right? So now, what is d upon d square plus r square raised to half? Look at this. What is d? This. And what is d
Cos
square?
theta.
Cos theta.
Yeah, so what are you going to get in this place? Cos theta.
Cos theta.
So 1 minus cos theta. This is basically the entire flux due to the disk. This is the flux of the entire disk, okay, at the point P, okay, towards x-axis. Okay, is there any doubt? Any doubt at all? Anyone? Anyone? No doubt?
Sir, why did not we consider here lambda?
Lambda, okay, charge per unit. See, actually what happened? Lambda is considered when you're taking in terms of length per unit area. Okay, a charge per unit area, charge per unit length. Okay, charge per unit area, charge. But here we didn't need to take, no? Here, what was I need to take? We know that what is dA? What is going to be dA? See, I know that E is equal to, see, what is the formula for this flux? d phi is equal to E dot dA. Okay, I'm not taking dE. Wait, 1 minute. It's not clear. d phi is equal to E dot dA. Okay, so E is what? KQ upon R square. E is what? I'll just rub this entire thing. I'll explain that now. E is what? KQ upon R square, no? Into dA. If it was dE, I would have taken K dQ upon R square. And then I can take that lambda is equal to charge per unit length. And then I can say that charge is equal to lambda times the length. And then dQ is equal to lambda into dL. Okay. You understood?
Yes, sir. Yes, sir.
So since I didn't take since d phi is equal to E times dA, I just put KQ upon R square instead of K dQ upon R square. That is okay. Ultimately, by putting KQ upon R square into dA, what you will get as a limited what you get in terms of a small element, that is going to be what? Instead of dA, what I had taken 2 pi x into dx. So ultimately, my variable is dx and x. Okay, not q. Okay.
Yes, sir.
Yeah. So now, everyone, just listen to me. We are getting into Gauss law. Okay. Just quickly listen. I will give you the entire theory. Listen. Now, what is Gauss law? Till now, what we were finding out? We were finding out what is the flux. We found out what is the flux due to a point charge. Okay, we found out what is the flux through a disk. We found out what is the relationship between a solid angle, plane angle. We found out the flux through open surfaces, closed surfaces. Okay, that is we found out this what happens. What is the flux through cuboid? And now, if you look at what Gauss is telling, okay, Gauss has a simple definition. What he says is simply that total flux that emerges out from a closed surface, considering that this is a closed surface. Okay, so the total flux which is emerging out of this closed surface, always remember, is what? Is equal to 1 by epsilon naught times the total charge enclosed by that surface. He's simply saying that the total flux, okay, that is, if I write it here, total flux, you can write total over. Okay, total flux is equal to what? 1 by epsilon naught times the charge enclosed by this surface, and that I will take as Q naught. That I will take as Q naught. So right now we know how to find out flux. Till now, what we were doing is we were finding out flux. And so now things become very easy for us. Okay. So I will tell you something. So how can you write it in terms of, you can write it as total is equal to charge upon epsilon naught. Okay. Is this clear? And this Q is the charge enclosed by the surface. Charge enclosed by the surface. There are many misconceptions here, which I will like to clear in some time. Okay. So what is everyone clear? Is everyone understanding this point? Okay. So suppose there is one small, surface over here, and there are several charges over here. Q1, okay, Q5, there's Q2 over here, there's Q3 over here. What is Gauss law saying? That he's telling that the total flux that is emerging out. What is flux basically? It is when electric field lines pass through a certain amount of area. when electric field lines are passing through a certain amount of area, and the electric field lines passing through that area, that entire area is called the flux. Okay, so the total flux, that is the amount of electric field lines coming out through the area, will be equal to what? The flux, the thing which has caused the flux to emerge out. And the thing which causes the flux to emerge out is the charge enclosed by the surface, okay, into 1 upon epsilon naught. Okay, is that clear?
Yes, sir.
Yeah. So now
Yes, sir.
let's do a small derivation. Okay, what is the electric field due to a point charge? See, again we are coming to this electric field, but this time we are using Gauss law. Electric field due to point charge. Okay, pay attention here. Okay, it becomes very easy. Suppose there is a charge here Q. Suppose there is a charge Q. Okay, what is a Gaussian surface which I will take around this charge? Okay, what is a Gaussian surface which I will take?
Sphere.
Yeah, I will take a sphere. Is everyone able to imagine that the surface around this sphere? Okay, I will explain what is Gaussian surface. Now just imagine, just for now. Listen to me. Okay, just for now. I am going to imagine that there is a sphere, okay, surrounded by this small charge Q. Okay, and now you want to find out the electric field, or you want to find out, yeah, the electric field at this point. What I will do is basically I will take a small area. I will cover this red. Okay, I know that this charge is emitting electric field lines and it is going to be perpendicular like this. Okay, and so E will be like this. Okay, is that clear? And now what is the small area vector area going to produce? It's going to produce an area vector. And in which direction is it going to produce? Area vector is always perpendicular to the surface. Remember this. So I am finally going to get an area vector which is going to be perpendicular to this area. Okay, to this small area, and I will write that as dA. Okay, I will write that as dA. Okay, I will write that as dA. So why I am writing it as dA? Okay, why I am writing it as dA? Because I am taking a small element. Okay, I am taking a small element. Okay, so now tell me what is going to be the electric flux using Gauss law. Basically, we know that d phi is going to be what? E into dA. Okay, E dot dA. And what is going to be, if I open this dot product, what is going to be? E dA cos theta. And cos theta between both of these, that is electric field lines and the area vector, is going to be 0. So cos 0 is what? 1. Ultimately what you'll get? EDA. Okay, but what does Gauss law say? What does Gauss law say? Gauss law simply says that the total flux which we have just found out, which is EDA, is equal to Q times upon epsilon naught. Is equal to Q upon epsilon naught. So I can write that the integration, see, this is d phi. D phi is giving me what? EDA. And so total flux will be what? Integration of d phi. Okay, total flux, that is phi, is going to be integration of d phi, which I can write it as integration of EDA. Okay, integration of EDA. And this integration of EDA is going to be equal to what according to Gauss law? According to Gauss law, what is it going to be?
Q by epsilon naught.
Q by epsilon
Yeah.
naught.
So I will rub this. Okay. So integration of, okay, one minute. Okay, just, yeah. Integration of EDA is going to be equal to Q upon epsilon naught. Okay, Q upon epsilon naught. And so now what we can say is that E is constant, electric field is constant, and I will tell you why electric field is constant. See, exactly. Around this Gaussian surface, if you take any small amount of element, it is going to be what? Perpendicular to the surface. It is going to be perpendicular to the surface. At any point, you take a electric field, you take a small area over here. Okay, electric field through this small area is going to be perpendicular to it. Electric field, okay, like this. Electric field through this small portion over here is going to be perpendicular to it. And so at every point, what is going to happen is, okay, E will be perpendicular to the surface. So I can say that E is constant. So I will just remove E out. I will remove electric field out. And so I will get E into integration of dA, which is equal to Q upon epsilon naught. Okay. What is dA now? What is dA?
Area of the sphere.
How much is it?
4 pi r square.
So what is E equal to? Okay. E is E into 4 pi r square is going to give me what? Equal to Q upon epsilon naught. Okay. Q upon epsilon naught. And so E will be equal to what? E will be simply equal to Q upon 4 pi r square epsilon naught. 4 pi r square epsilon naught. Okay. This is the electric field intensity. Okay. Due to a point charge using Gauss's law. Okay. This is the electric field intensity due to a point charge using Gauss's law and using with the help of a Gaussian sphere. With the help of a Gaussian surface. Okay. Is that clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Yeah. Now one small thing. Application of Gauss's law. Okay. Let's see. Total flux that is enclosed within a surface should be okay. Total flux within a closed surface. Okay. It's always zero if the point charge is out. Look here. This is important. Tomorrow, if anyone asks you this question, you should know. Just simply. Okay. If they give you any shape, doesn't matter. If it is a closed surface, imagine this is a closed surface, like a sphere, it is a closed surface. There is a point Q outside. Okay. This point Q is basically emerging electric field lines in every direction. Let's say this side, this side, this side, this side, and this side, this side, this side, this side. So now if I tell you to find out what is the electric flux through this entire area, what is it going to become? Okay, what is it going to become? It is going to be zero. For those who don't know, listen to me. Electric flux, okay, field lines which are passing out of this surface will be equal to the electric field lines which are passing entering inside the surface. So amount of electric field lines going out is equal to amount of electric field lines entering the surface. And so flux entering is equal to flux going out of the surface. So the entire flux is going to become zero because the net flux is zero. Okay, outside minus inside. Flux emerging out minus the flux entering inside the surface. Okay, this is clear. Next statement is simply that the surface integral. Okay, what is the meaning of surface integral? What is the meaning of surface integral? Whenever you are integrating a particular surface, let's say dA, okay, and it is a closed surface. Okay, if it is a closed surface, we will show it in terms of a small sign around the integration, and that is this. This simply means that it is a closed surface. Okay, and whenever you are applying integration over a small using a small element in a particular surface, you are basically trying to integrate the entire the entire element over the surface. You take a small surface like this and you're taking a small element like this. Ultimately what you're going to do is, if you're going to integrate it, you're taking this and repeating it 1,000 times unless and until the entire surface is filled. Okay, that is what integration is. And so basically you covered the entire surface, so it is simply called surface integral. You need to know this because I'm going to tell you a small definition that simply says, okay, a small definition that says the surface integral over the electric field. Okay, surface integral of the electric field due to all the charges, okay, over any closed surface is 1 by epsilon naught times the net charge of enclosed by the surface. Look here, if there is, this is one small misconception I want to clear. This is a small surface. There are many charges out. Q1, there's Q2 here, there's Q3 here. There is some in the inside, Q4, Q5, Q6. What you should know is that, okay, the total flux is not just dependent on this on the charge which is inside the surface. Okay, the definition says that the total flux is just not because of this, it is entirely because of all the charges around it and inside it, both outside and inside. Okay, so the definition will tell you the surface integral of the electric field due to all the charges, okay, both inside and outside the sphere over any closed surface is 1 by epsilon naught times the net charge enclosed by the surface. That means that the entire flux, okay, you're taking a Gaussian surface around this area. Okay, you're taking a Gaussian surface. Considering that this outside thing is a Gaussian surface, then what will happen is the definition is telling me that the total flux emerging out of the surface is equal to q upon epsilon naught time, where q is the charge enclosed by the surface, but is also because that entire thing is also because of the charges which are present even around the surface. Always remember that. Okay, it is not that only the charges inside, just because you're considering only the charge enclosed by the surface, that the total flux is only because of this. The total flux is not just because of this. The total flux is basically contribution of all the charges which are inside the surface as well as outside the surface. That, okay, ultimately what happens is the entire surface, the entire flux is given as, according to the formula, it just comes out to be enclosed, that the entire flux will be equal to, even though it is a contribution of all the charges around it and inside it, the entire flux will be equal to the charge enclosed by the surface. Okay, that is clear. Is that clear?
Yes, sir.
I hope you all are hearing. Okay, so ultimately phi, okay, ultimately phi E dot dA, which is basically the flux, is going to be what? Addition of all the charges upon epsilon naught. That is what q1, okay, q5, q6, q4, charge enclosed. That is q5 plus q6 plus q4, entire thing upon epsilon naught. Okay, because charge is scalar, so it can be added. Okay, is that clear?
Yes, sir.
Yes, sir.
Right. Okay. So one small thing before before the class is going to end, I think there's only going to be 5 minutes. I want you to find out, if I put two charges, okay, if I put two charges inside a Gaussian surface, let's say q1 and there's q2, okay, and considering q1 as plus and considering q2 as a negative charge, what is the entire flux equal to?
Q1 plus Q2 upon epsilon naught.
Okay, q1 plus q2 upon epsilon naught. Any other answers? Tell me fast, the class is going to end. There's only 5 minutes. I've already got a notification.
Q1 plus Q2
Fast.
upon epsilon naught.
But see, look here.
Q1
Q.
minus Q2
Yes,
upon
someone is. Yes. So
Q
Q1
minus
is
Q2
what?
upon epsilon.
Positive. Yeah, but Q1 is positive. Q2 is negative. So what is going to happen? What is going to happen? What it will be entire flux equal to?
0.
Zero. Zero. So always remember, this small concept is called dipole. Okay, I will get into dipole very fast, but all you need to know right now is that if there is a dipole, okay, that is a positive charge and a negative charge brought together inside a Gaussian surface, okay, that will be, the entire flux is going to be equal to 0, because all the electric field lines produced by this charge q1 is going to be consumed by q2. All the electric flux field lines which are going to be produced by q1 is going to be consumed by q2, and so ultimately the total flux which is emerging out of this